Okay. So can you see me and hear me?
Yeah.
Okay, I'm going to start. So I'm going to deal with amines, and carrying on from the small amount of time we had last time, can I reiterate a few things I said there, and then we'll carry on with new things this morning. Amines are ammonia derivatives. So this is ammonia, and ammonia you should be familiar with. You can see that ammonia has a lone pair of electrons. That lone pair of electrons gives it two main personality traits that I want you to focus on. One, the lone pair will make it a base. So that lone pair will be available to make a dative covalent bond elsewhere, like a proton. So the Lowry-Bronsted theory of acids and bases, the Lowry-Bronsted theory talks about proton acceptors of bases, and so the proton can be accepted using that lone pair onto the nitrogen. The second trait is something that we can go back to haloalkanes topic, and the second trait is that ammonia is a nucleophile. So it can do nucleophilic substitution, but if you go back to haloalkanes, ammonia was used with, I think it was bromomethane, that we had methylamine formed as a consequence using excess ammonia. Now I'll be talking about that reaction later today. So I want you to know that it's a base and it's a nucleophile. Now, obviously, if we talk about it being a base, then it's a weak base. Ammonia is a weak base. And all these amines we're going to talk about today, they are weak bases, and we're going to talk about the base strength. Indeed, that's where I would like to start. I'd like to start talking about the base strength of amines. So let's just firstly talk about a very important reaction that happens with amines and happens with ammonia. Are you familiar with it with ammonia? I just need to make it absolutely clear to you how it's a base like this. So say we have a H plus.
Adjust the camera because we can't really see.
Sorry, just will you say anything?
Oh yeah, we can't really see the projector fully.
You can't see the projector if I'm talking to you?
No.
Can you see it now?
No, it's still the same.
You can't see it now. Okay, sorry. It's a problem if you just can't see it. When I looked, I thought that was quite a good view. Is it clear now?
If you can adjust it a little bit more, that would be better.
Adjust it. I'm not sure how. All I'm doing is changing the position. I don't know how else to adjust it.
Yeah, that works. Yeah.
Is that better?
Yeah, that's better.
Okay. So what I'm trying to draw for you is, if you have a proton with ammonia, then you can get a dative covalent bond happening like that. The example is having a real acid. You can have a range of acids. You don't have to have one particular acid. Obviously, a base with an acid will make salt and water. So the reaction I want to talk about is having ammonia with hydrochloric acid will make ammonium chloride solution. Now, ammonia, is that better? Ammonia is a weak base, but hydrochloric acid is a strong acid. So that reaction will go to completion. That reaction will go as far to the right as is possible, limited by how much ammonia and how much hydrochloric acid you've got. However, this next reaction, ammonia with water, will make ammonium hydroxide solution. Now, that arrow there should not be a proper arrow. A proper arrow like that shows that the reaction is going to the right. And you guys know that ammonia as a weak base will partially turn into ions when dissolved in water. So that's water is being dissolved in water. It will partially turn into ions. How do we show that? Well, you need to get rid of that. And you need to substitute it with a reversible arrow. The reversible arrow will show that typically just a few percent of ammonia will turn into these ions. Now, some of you may query, that doesn't look like ions, but that is ionic, and it is in fact made up of ammonium ions and hydroxide ions. And typically 1%. So typically 1% of these ammonia molecules, when you dissolve them, will make these ammonium ions and hydroxide ions. So what about the remaining 99%? Well, the remaining 99% will stay as the molecule. The remaining 99% will stay as an ammonia molecule. So ammonia solution will have 3 main ingredients within it. Actually 4. So let's go through them. Ammonia solution will have mainly water molecules. Then a lot of the ammonia that you start with will still be ammonia molecules. So ammonia molecules will be present. So those molecules, water and ammonia, will be there in abundance, lots of them. These next 2 ingredients are the ions, and there will not be many of those compared to how many molecules of ammonia and water you've got. So you'll have the ammonium ions. The ammonium ions are that reaction, the reaction there at the top, where that's how you get the ammonium ions. And then you've got your hydroxide ions. And your hydroxide ions, if you go back to your year 10 chemistry, alkalis were things that would give us hydroxide ions when dissolved in water. So that was the Arrhenius definition. So we know ammonia like that. We know it's a weak base. We know it's an alkali. We know that when we have solutions of it, you've got lots of ammonia molecules and you've got some ions. Now, all of those things that I've said with ammonia, all of those things apply to amines. So the amines themselves, they will, in the same way, they will react with acids, making salts. Amines will react with acid, making salts. Amines will dissolve in water to different extents, solubilities. They'll dissolve in water and they will make these ions. And again, you will get questions in the exam that will require you to write equations, and I want you to think of these as bases. Amines are bases. Let's turn this off. Amines are bases that will make salts when you react them with acids. With water, they will give you low concentrations of hydroxide ions and behave like alkalis. Okay, so let's turn now to the base properties and just talk about how basic the amines are compared to ammonia. So our starting point is ammonia that we've talked about, ammonia that we're familiar with. And what we want to do is we want to compare amines. Are they more basic or are they less basic? And this is a discussion that they ask about quite a lot. So I need you to pay particular attention to this next bit, and I'm going to run through it. Now, as it was clear that the base properties result from the lone pair of electrons, then clearly it's all about that lone pair of electrons. Each of these discussions I'm going to go through, and I'll go through 4 of them. Each of the discussions centers around looking at that lone pair of electrons. Now, I've not drawn an amine yet. So let me draw one amine. I'm going to start with a primary amine, and probably the most used primary amine is ethylamine, ethylamine. You could, the same discussion I'm about to have applies to methylamine or propylamine. The pronunciation is more like methylamine, ethylamine, propylamine, butylamine, and so on. But let me draw one and then we can talk about it. Now, ethylamine. One property of this that you should be familiar with, my pen's not working very well. One property of this that you should be familiar with is that it has a positive inductive effect. So let me talk through that. If the ethyl group has a positive inductive effect, which it does, what does that mean? Well, it means that it will push electron density away from itself. So if you picture that ethyl group pushing electron density, pushing it away from itself, then it's pushing it onto the nitrogen. Now the nitrogen's got that lone pair of electrons. And that lone pair of electrons, as I've been saying to you, is the cause of the basicity, the availability of that pair of electrons. So if more electron density is being pushed onto the nitrogen, then there's more electron density around the nitrogen that will in consequence make the lone pair of electrons more available for bonding. If that lone pair of electrons is more available for bonding, then we can do a direct comparison versus HNH2. Directly, that's ammonia. If the H is an alkyl group, then that pair of electrons compared to ammonia, and we compare it with ammonia, compared to ammonia, that will be more basic. It will be more of a base. The equilibrium that I talked about, this equilibrium, let me draw it again. C2H5 NH2 plus water, equilibrium arrow, C2H5 bond NH2 with a new H positively charged and OH minus. So that reaction will be more over to this side. The equilibrium position will be over to the ions more than if it was ammonia. So the base properties of primary amines. Let's turn this off so I can talk to you a bit more. The base properties of primary amines are that they are more basic. Their base strength is more. That dissociation into ions is a bit more. Not vastly more, just a bit more. So if we take ammonia as a weak base, then primary amines are better bases, slightly. They're more basic. So what are secondary base? Well, no, actually, before I leave primary bases, let's discuss one more discussion. What about the size of this? The size of the alkyl group. What if you've got CH3 NH2? Or what if you've got C3H7 NH2? So that's methylamine, and propylamine. Then I want you to know that the size of the alkyl group, has an effect. And the size of the alkyl group has an effect because the positive inductive effect of larger alkyl groups is more pronounced. The positive inductive effect is more for larger groups. So with methylamine, that's a smaller group. So methylamine will be a weak base than ethylamine. What about propylamine? Well, that propyl group is a bit bigger than the ethyl group, and therefore propylamine will be a little bit stronger as a weak base. Don't forget, don't use the phrase strong bases. You must call them weak bases. But within the sphere of weak bases, within that group of weak bases, you can talk about having stronger weak bases and weaker weak bases. And the size of the alkyl group will affect the availability of that pair of electrons because of this inductive effect I've been talking about. And as a consequence, the base strength will then be different. So if you are asked to compare the size of an alkyl group attached to NH2 as a primary amine, then you must use these arguments about the larger groups have a more positive inductive effect, and therefore they are a little bit stronger as weak bases. Okay, so that's a discussion. That's the first discussion with primary. Then we can move on to the discussion with secondary amines. Now, this should be obvious now. If you've understood the first discussion, what about secondary amines? Now, to remind you what they are, they're those. Instead of having one alkyl group, we've got two alkyl groups. So two alkyl groups. Now, using exactly the same arguments that we've come across previously, then again, it's exactly the same argument. The pair of electrons on the nitrogen that give it its base properties is what we have to concern ourselves with. But now with secondary amines, you've got two alkyl groups. Each one Each one of those is pushing electrons towards the nitrogen. So you've got double the positive inductive effect that you would have on the first when we talked about primary amines. So compared to primary amines, secondary amines will have more electron density around the nitrogen as a consequence of two alkyl groups pushing electrons onto the nitrogen, and that will make that lone pair on the nitrogen even more available, and therefore they are better bases. Secondary amines are better bases than primary amines. The discussion is very similar to primary, but two alkyl groups. What about tertiary amines? The third discussion would be exactly the same, talking about tertiary amines. Well, tertiary amines would have three alkyl groups. So we can write tertiary, abbreviate it like 3 degrees. So 3 degrees, when we write it, stands for tertiary. Here, same discussion again, all about positive inductive effects, but you've got 3 alkyl groups. All of those 3 groups are pushing electrons towards the nitrogen. The electron density around the nitrogen will then be even more than it was there, or with the primary, and consequently the tertiary the tertiary amines are better bases than secondary, which are better bases than primary, which are better bases than ammonia. So we can, using these arguments, we can build up a picture which, if I get to my pen, we can talk about base strengths. So, compared to ammonia, NH3, RNH2 is a primary. Primary amines are better bases. How about R2NH? They are secondary. They're better bases. R3N are tertiary. So these are, if I get a different color, primary, secondary, tertiary. And compared to ammonia, so the pattern you need to learn is base strengths. Primary are better bases than ammonia. Secondary are better bases than primary, and clearly better than ammonia. Tertiary are clearly better bases than secondary amines. Tertiary amines are better than secondary, secondary are better than primary, primary are better than ammonia. And it's all about the availability of that pair of electrons on the nitrogen. So I want you to learn that. I want you to learn that pattern. And then I also want to talk about, what about having N, where you've got an R group, R group, R group, and what about another R group? What about these quaternary ammonium ions? Are they bases? Well, what I'm hoping that you realize is the discussion has all been about a lone pair of electrons. And the lone pair of electrons is not available because that lone pair of electrons on a quaternary ammonium ion has been used in making a data covalent bond with a fourth alkyl group. So where you've got quaternary ammonium ions, don't fall into the trap of thinking that they are bases, because bases need to have a lone pair of electrons with which they can accept a proton, etc., and do the base properties that we talk about. So bear in mind that quaternary ammonium ions are not basic, that tertiary, secondary, primary, and ammonia have that pattern that's up there on my overhead projector. And then on top of that, if they ask you questions about base strength, how basic something is, then I want you to bear in mind that the size of the alkyl group matters. So NB, just got this big, horrible red pen. NB, size of the R group matters. So I want you to realize that in exams, they'll ask you to compare different amines. They'll give you tertiary and a secondary and ask you which is the better base. However, they will also ask you the question, say it's a secondary amine, and give you two secondary amines and ask you which is the better base. Now that's not going to be easy to answer unless you realize this point about size matters of our R groups, because the bigger the group, the more the positive inductive effect pushes electrons, and therefore the bigger groups, if you've got two secondary amines, one of them, the R groups are a bit bigger than the other, then the bigger group, the one with the bigger R groups will be the better base, because the positive inductive effect will be slightly better if the group is bigger. Now, I know I repeated myself many times, but I hope you appreciate that my repetition is my attempt to explain to you the importance of the points that I'm making. So, what else? Well, I want to talk about the R next. That R, alkyl group. That R, alkyl group. That R, alkyl group. Where we've got normal alkyl groups like methyl, ethyl, propyl, butyl, pentyl, etc., where we've got normal groups, turn that off. Where we have absolutely normal groups like that, those things are called aliphatic amines. Aliphatic, I've explained in previous lessons, does not involve benzene groups. So to finish off the discussion, we have to bring aromatic amines into our discussion. And bringing aromatic amines in will give quite an involved discussion, and I'm about to deliver it. And it will fundamentally, having a benzene ring next to the nitrogen, will fundamentally affect the availability of that pair of electrons. So we always have to get back to the availability of that pair of electrons. And aliphatic amines are weak bases. But aromatic amines, now careful, because we'll do a couple of examples. By aromatic amines, we mean having an amine where the benzene is directly linked, directly attached to the nitrogen. And in that way, when the benzene ring is directly attached to the nitrogen, then this following discussion applies. So I want you to know that all of that discussion up there, aliphatic amines, right? Now we're going to talk about aromatic amines. And the most famous example, aniline, phenylamine. Let me draw it like this. Pair of electrons. Right. That is an aromatic amine. It's a primary aromatic amine. I hope you understand that term, primary, NH2. One of the hydrogen positions is occupied with the benzene ring. For me to carry out this discussion with you properly, I need you to understand the structure of benzene from previous lessons. Now you should know that that ring, let's turn that off, I'll turn it back on later. You should know that the benzene ring has got 6 electrons. Those 6 electrons are delocalized. The delocalization spreads across those 6 carbon atoms within the ring. But now I want you to ask yourself, what is next door? Where the nitrogen is attached, you've got like the carbon-nitrogen bond, the carbon being part of the benzene ring is attached to nitrogen. The nitrogen's got that lone pair of electrons that we need to talk about. So if I draw in the p orbitals in that diagram, what I'm hoping you'll see is that these 6 electrons, together with the 2 lone pair electrons, those 8 electrons now become delocalized, not just in the ring, but the delocalization will spread from the ring onto the nitrogen atom. If the 2 electrons that we've been talking about, the availability of that pair of electrons, those 2 electrons get involved with the delocalization of the benzene ring. And if they do, then the delocalization now involves 8 electrons, and there will be a stability associated with those 8 electrons and that delocalization that happens, which I'll draw in a minute. That will reduce vastly. That will reduce significantly the base properties, that is the availability of that pair of electrons to make a data covalent bond. It will reduce the ability of the molecule to do those base reactions, and therefore aromatic amines are fundamentally much weaker weak bases than ammonia. So let me try and draw in the p orbitals to hammer home the point. So there you've got p electrons like this. And we can talk about having delocalization happening above and below the ring. So here the p sticking up perpendicular to the plane of the atoms, the p orbitals sticking up and then overlapping, going back to the benzene structure we've talked about in the past. You know that those 6 electrons will do that. Now what I want you to do is to know that these 2 electrons, those 2 electrons, they are p electrons as well. and those can get incorporated. If I draw the p orbital like that again, the p orbital electrons can get incorporated into this delocalization that we've talked about in the past, so that the delocalization spreads. It will spread from the benzene ring like that. So the delocalization incorporates the two electrons, and the delocalization spreads across onto the nitrogen. Fundamentally, then that pair of electrons is not as available. The lone pair is therefore less available for bonding, such as accepting a proton, etc. So if it's less available for bonding, such as accepting a proton, etc., therefore aromatic amines are weaker. They are weaker weak bases. Aromatic amines are weaker weak bases because the pair of electrons on the nitrogen that we need for it to be a base become involved in the delocalization. And as they become involved in the delocalization, they're less available for bonding. As they're less available for bonding, then that fundamentally means they will be weaker weak bases. Okay? Okay, so in order, what do I want you to know overall to summarize? Aromatic bases are weaker bases than ammonia. Secondly, aliphatic. Aliphatic are stronger weak bases. Aliphatic are stronger weak bases than ammonia. Third point. Primary are better bases, stronger weak bases than ammonia, but secondary amines are stronger weak bases, still stronger than even primary amines, and tertiary are stronger weak bases still than secondary, all due to positive inductive effects of alkyl groups. Fourth point, the size of alkyl groups matters. The more alkyl groups, then you have more of the, if it's to do with size of the alkyl groups, the bigger the alkyl groups, then you have more positive inductive effect, pushing electrons away, pushing electrons toward the nitrogen, because bigger groups have that effect than smaller groups that are alkyl groups. And therefore you can compare the base strengths of aromatic, ammonia, aliphatic, primary, secondary, tertiary, involving different size alkyl groups, etc. Okay, I'm going to stop the recording there and I'll take questions. Stop the recording.